Okay, so more or less this is the plan. I don't want to spend much time about it. So what are these categories of cobordism? As I just said, they are categories whose objects are compact, oriented, n-dimensional manifolds. Now, for this talk, n, you can choose it to be 2 or 3. So I will be talking about n and replace it with 2 or 3 according to your preference. And actually, there will be a distinction only in the last part, where, of course, in n equals 3, so the higher dimension, something new happens, and there will be something more to say. But until almost the very end, you can freely pick your favorite value. And morphisms are cobordisms. So this means n+1 dimensional oriented compact manifolds with the boundary which is parameterized by 2 given objects, okay? And the composition is given by gluing the manifolds along the common, I said surface, as you see. I had in mind n equals 2 k's, but same definition for n equals 3. I just want to mention that this is what people normally call cob n, okay? This is the category of n-dimensional objects and n+1 dimensional cobordisms. There is another category I shall call cob n nc, nc as non-compact. It means it's basically a subcategory. It is a subcategory of cob n, but you require the following restriction on the cobordisms. You require that for every cobordisms, every connected component has to have non-empty negative boundary. The choice of negative versus positive is purely conventional, but that's the choice we made, okay? So it's actually the cobordisms are compact. So the word maybe is not well chosen, but it's not us who chose it. Actually, that already appeared in Lurie's work on the cobordism hypothesis. So we adopted the same term. Let me also mention that it might look as a funny restriction, but actually, if you think about it, basically all the topology is already in cob nc. Okay, so if you're interested, for instance, in closed for manifolds, let's say, okay, you might say, oh, but a closed for manifold is not in cob nc. It cannot be seen as a cobordism from the empty to the empty because it doesn't satisfy this restriction. So it's bad. You cannot deal with closed for manifolds. Actually, this is not a true problem because for every manifold, you can canonically take out a ball, local ball, a small ball, and you get a manifold with boundary, which you can think of as a cobordism from the sphere to the empty. And actually, what I just said is a canonical operation by a theorem by Palais in general for n-dimensional smooth manifolds. Every n-dimensional ball is isotopic to the nice little ball you can take out of a nearer point. So that's canonical. So in truth, you're not losing anything. Yes?
Are you smooth or are you topological? Or
Even, would I just say Palais' theorem is for differential manifolds, so smooth.
So you're smooth. So you're smooth.
Yeah, I'm smooth. Yeah, I'm smooth. Anyway, so I'm smooth. You can see, since I'm working in dimension 2 and 3 or 3 and 4, smooth equal PL in both cases. Smooth is not equal topologically in dimension 4, but it's not my case here. Both these categories, be it cob n or cob n non-compact, are monoidal and symmetric. So the monoidal is just a disjoint union, the monoidal product, the tensor product, and the symmetry is just the exchange. So there's nothing surprising. If you've worked with cob n, you should not be scared of cob nc. But the only difference, which actually makes a big deal, is the fact that cob n is rigid, namely for every object, you can always find the dual of the object, which is just the same manifold with the opposite orientation. And the fact that the second one is a dual of the first one is witnessed by the existence of n+1 cobordisms, which realize the evaluation and coevaluation map in the categorical sense. And these n+1 manifolds are just products of your initial manifold, like this or like this. So this is the evaluation, this is the coevaluation. I'm really very much waving my hands, but I think you all understand what I'm doing. This is not happening cob nc because this is forbidden. This would be a a cobordism from the empty. I read the cobordism from the bottom to the top. This would be a cobordism from the empty set to something else. So it's forbidden incumbency. Therefore, objects are not automatically dualizable incumbency, which prevents the proof of the fact that a TQFT has always finite dimensional images as vector spaces. This is no longer true for a non-compact TQFT. What is a non-compact TQFT? It's a functor from Coben C instead of Coben, two vector spaces. Yeah, monoidal symmetry.
It has Grothendieck-Verdier structure.
Excuse me?
It's not rigid, but it has Grothendieck-Verdier, maybe.
No.
No, not even.
I wouldn't think so. I wouldn't think
I
so.
mean, like because
It should be, you need a dualizing object.
Yeah, exactly.
Non-trivial dualizing object.
same tensor unit. I mean, empty.
Yeah,
Yeah,
there's nothing
that's
but the
for
empty
Coben.
set.
Coben, yes, but Coben C.
Yeah, but then it would be an R category in the terminology of Lyubaschenko-Hennings. That restricts the structure quite a bit.
I don't expect it to be. I don't see what the dualizing object could be. In Coben C. But I could be. I'm not expert in Grothendieck-Verdier. So finally, a n-TQFT, what I would call an n-TQFT, is a symmetric model functor from Coben to vector spaces over your favorite field, and we call it compact. Okay, compact because it uses this category, and so everything is accepted. And then we call it non-compact if it's actually a symmetric model functor from this subcategory to vector spaces. Okay. Any questions? So let's overview rapidly some examples of these things. For n equals 2, meaning again surfaces n 3 manifolds, there is a very famous Turaev construction. They did it in a sense by hand at the beginning in their initial paper for the category associated to SL2, quantum UQ-SL2, and then it was generalized by Barrett and Westbury for general categories with a certain structure, which is now known as spherical structure. These categories in Barrett-Westbury's approach are K-linear, and they are mainly, that's the important thing, they are semi-simple. What I'm going to talk today about is the same story, basically, but remove the semi-simple condition. And it happens that as soon as you remove this semi-simple condition, there is a natural notion of spherical category. Actually, I should define it for you, and I will later. And you get Turaev theories, Turaev-like theories, but for associated to these algebraic data. And the price to pay is that you have to restrict yourself to NC, non-compact cobordisms. It's actually, as I said before, it's not a big price to pay. And actually, you get interesting stuff. I hope to convince you about this. In dimension 3, so meaning 3 manifolds are the objects, 4 manifolds are the cobordisms. There is the famous Crane-Yetter theory, Crane-Yetter-Kaufman. Crane-Yetter defined invariants, and with Kaufman realized it could be extended to TQFT. But unfortunately, it is well known that it is kind of not sufficiently interesting from a topological point of view because it is invertible. What does it mean to be invertible? It means that the vector space associated to each closed 3 manifold is just a one-dimensional vector space, and the linear map associated to any 4-dimensional cobordism, it's an invertible linear map. This is what people call an invertible TQFT. And as a consequence, this is going to be too trivial. The invariants you get for 4 manifolds are too trivial. They cannot detect the interesting phenomena happening only in dimension 4 and not in dimension 3, like existence of homeomorphic but not diffeomorphic 4 manifolds. So in a sense, it's disappointing.
In the case that I am braided, does your definition of spherical is the same as ribbon?
So yeah, spherical for me doesn't require a ribbon. As soon as I pass to n equals 3, the input will have to be ribbon by a
I'm just saying, so you're saying you have a generalized notion of spherical, which is chromatic.
Yes.
And so, and at least in the fusion case, I would expect spherical to be the same as ribbon in the presence of the braiding.
No, ribbon is braided.
Ribbon is
So that's what I'm saying, in the presence of the braiding.
Oh, what's breaking?
So, I mean, this chromatic thing is the existence of a certain, I will tell you later, the generator and with a certain morphism, which can be applied to just a pivotal category. In that case, we call it spherical, not semi-simple, so spherical, or it can be applied to a ribbon category. And in that case, we have a ribbon chromatic category. So it's, in a sense, it's independent of ribbonness or not. Did I answer your question?
It's a terminology question, but it's not, yeah. It's
Okay.
Ribbon usually assumes spherical.
Ribbon.
It's balancing and then this pivotal structure which is spherical at the same time.
Yeah, but okay. So I'm using spherical here in Barrett and Westbury's sense. So in particular, I mean semi-simple. And you are using spherical here just to say that left trace and right trace are equal, which is less than, you don't require semi-simple in saying that.
Don't have to.
So okay, yes. Then we agree. Okay, so today I will talk about this n equals 3 case. So we use this notion of chromatic category. And what I want to stress here is that probably it doesn't come as a big surprise, the fact that from a modular category you get a 3+1 TQFT. This is the Crane-Yetter-Kaufman theory. What is interesting here is that actually we don't need modular. It strictly goes beyond the modular case. I'm not saying that we got topologically interesting stuff yet, but I'm saying that there is hope for that. So actually, I plan to keep working in that direction. So this bold part here is actually probably the main message of the talk today. So one can go beyond the modular case and still get interesting TQFTs. Okay, I want to mention that actually our construction is related to other constructions. Anna and Marco have built a functor, which you can call a TQFT, albeit from a different category. It's not the category I called COB3. It's a category of three-dimensional endobodies and their four-dimensional cobordisms of a special kind, namely those which can be built out of 0, 1, and 2 handles, but no 3 handles, no 4 handles are allowed. So in a sense, it's different, but the spirit of the construction is very much similar. And I must mention that Kevin Walker has spoken since a long time in his notes about a semi-simple approach, very similar to what we did in the non-semi-simple case. And then he also announced with David wrote a work doing the non-semi-simple case, but as far as I know, the work is not yet available online. You might be asking yourself, where is Reshetikhin-Turaev here? And I've been talking only about Turaev-Viro, and Reshetikhin-Turaev is missing. I will not be talking about it today, but let me mention the following. You've seen it probably in other talks. In truth, Reshetikhin-Turaev is not a TQFT in the sense I gave you. Because the truth is that the starting category, the source category, is not COB2, it's COB2 with a certain decoration. I noted it COB2 sigma. So the decoration is the fact that these surfaces need to have some additional data, the data of Lagrangian in the H1, whatever it is, it's an additional combinatorial datum which is needed to resolve the anomaly of the TQFT. Okay, so in truth, Reshetikhin-Turaev is not a TQFT in the sense I defined previously, because the starting category is slightly more complicated, but the starting category has a forgetful functor to the category COB2 I defined for you before. Okay, so that's why I'm not putting this in the story today. Yeah, and these additional data are needed in order to basically the cobordisms are just the old cobordisms plus an integer. And these additional data are exactly to tell you how to sum the integers when you glue two cobordisms. You don't just sum them, you sum them and you add an additional term, which is computed out of the Lagrangian data. It's called the Maslov correction. Anyway.
Question on
yes.
Turaev. So in the semi-simple setting, we know the Turaev-Viro for spherical category C or spherical fusion category C is the same as Reshetikhin-Turaev for its center.
Yep.
Do you expect this to be true as well also for your non-semi-simple theories? compared to the non-semi-simple theories of the Renz, Geer, Patureau-Mirand, Runkel?
I should properly think about your question. It's a good question. I would expect yes, but there is work to be done because I would have to first show that if I have a category which is spherical in my sense, then I take a double, it's ribbon and spherical in my sense. So I think it's doable, absolutely, but I didn't sit down and think about it. That's a very good question. So suppose now we want to build a TQFT. How would you do? There's a nice strategy, which is based on the following theorem by Juhasz. So it's a Rust statement. I'm really trying to make it stay in 2 slides. So I'm a bit oversimplifying it. So my apologies to the author. So basically, it's a presentation for the category comp N, okay? Which means what? It means that it gives you a list of morphisms. So the objects, a list of morphisms, and the relation between those morphisms, okay? So what are the objects I told you before, they are n-dimensional manifolds. What are the morphisms, the generators of the morphism? There are 1 arrow, I noted EF, for every diffeomorphism F between 2 n-dimensional manifolds. Okay, I call it EF. There is 1 arrow for every handle you can glue on a n manifold. So what's a handle? It's an embedding of sk times dn minus k. Sk is the k-dimensional sphere times dn minus k into m. Okay, it's called an index k plus 1 handle. Whenever you have such a thing, you can do a surgery over that. Basically, you replace sk by a d k plus 1 and dn minus k by s n minus k minus 1. You do, well, you change your manifold, okay? You get actually gluing this handle, which it's actually half of the boundary of dk times dk plus 1 times dn minus k is the cobordism between 2 n manifold, right? And it's a cobordism obtained by gluing a single handle to the thickened 3 manifold. So the picture is more telling than what I'm saying, is that you have your 3 manifold, you just thicken it, and then you glue some handle. Here is where is s times d whatever, sk times d minus k, something minus 1 probably. Oh, not minus 1. Okay, and then you glue this, and then this is the new manifold you get, which I denoted M of the sphere. Okay. So these are the generators, and now they are subject to relations. The first relation is an obvious one. You want, if you have 2 composable diffeomorphisms, the composition of the arrows should be the arrow of the composition. Here. There's a second one, which is the following. If you have 2 manifolds which are diffeomorphic by a diffeomorphism D, and you're gluing a handle on the first one, you expect that if you glue the handle on the second one the obvious way, you would get diffeomorphic manifolds, and that's what I'm writing here. Okay. Third is that if you are gluing 2 handles but on different disjoint support, then you can do it in both orders and you get the same manifold, right? So you're asking commutation of the arrows associated to gluing handles. Also, this one is quite clear. Stop me if I'm going too fast or being too sloppy. The most important one is the 4. The 4 has already shown up in Anna's talk. The fact that there could be handles which cancel each other. Let me show you a concrete example. Suppose we are in dimension n equals 2. So I've glued a 1. This is a 1 handle glued on a surface, okay? And then I glue a 2 handle along this curve. So basically, what I'm doing is I'm regluing this disk here, and I filled it up. What I get here is just a sphere, just a bump on my initial surface. So I get back my initial surface. So that's an example of cancelling handle. More in general, the topological condition, the geometric condition is that the belt sphere of one of the two handles should intersect exactly once the core sphere of the other. Okay, if they do it, and they have index k and k+1. If they do, then the resulting manifold is isomorphic to diffeomorphic to the initial one, and that's the condition written here. And the last one is I will not talk much about it. You don't care how you orient your sphere. You can be oriented one way or the other. It's still the same handle that you're gluing, basically.
So where's handle sliding then?
It's coming from, if you think about it, handle slide is here, hidden here in 2, because the handle slide is just an isotopy of your manifold. So it's a diffeomorphism.
Cancellation is also diffeomorphism.
Excuse me?
Handle cancellation is also diffeomorphism.
Yes.
I don't get it. Why one is receiving the same condition and the other is not receiving it?
Can you speak louder?
People don't hear you.
Nobody
what
can
you say.
hear you.
No, I'm saying no. But here I'm using a diffeomorphism after one handle. Okay. I'm saying that it is the commutation of diffeomorphism. When you slide a handle over another one, you're actually operating a diffeomorphism from your manifold presented in a certain way to your manifold presented in another way. So I don't know if I'm answering your question. Okay, yeah, we can talk about it. Anyway, this is not my result, it's Juhasz theorem. Yeah, he was stating this is basically his theorem. He didn't care about Cobb non-compact, but actually, if you think about it, for Cobb non-compact, it's not much difficult to get a similar result where you basically have to disregard, or whenever 0 handles appear, you disregard the related operation. So you can easily get a similar presentation for Cobb and C. So how to, again, back to our question, how to build a TQFT using this theorem? Well, you need to have for every n-dimensional manifold a vector space, okay? And of course, you want this vector space to be acted upon by the diffeomorphism group of the manifold itself. And so that's what I write by, you want to associate a k-vector space equivariantly with respect to diffeomorphism. That's what I mean. It's not just a vector space. You can act on that vector space by the diffeomorphisms of the manifold, orientation preserving, of course. And then you need to know how to glue handles to your manifold. So I will count backwards. Might be disturbing at the first sight, but it's not, doesn't change it, right? You need to know how to glue n+1 handles, which means what? It means that if you have a component of your manifold, which is an n sphere, okay? Gluing an n+1 handle means that you glue a ball, a bn+1 to that Sn. So it disappears, that Sn, okay? That's an operation of gluing an n+1 handle. So you have, for instance, in dimension, so that's, for instance, gluing a 2 handle over a 1 circle, right? You make it disappear one sphere of maximal dimension. So you start by requiring having a linear map from the manifold before doing the operation to the manifold after doing the operation. If your manifold is just a sphere, you want to have a linear map from the vector space of the sphere to your field. Then you want to glue n handles, which corresponds to gluing, well, we'll have pictures later, but this is the operation. You replace Sn-1 thickened by a Bn cross S0. So this means, graphically, this means that you start with a picture which looks like this one. You start with a picture which looks like this one. And you have a tube. And then you cut along this sphere, and you replace by this. Okay, so you come back to your, in this case, you come back to your initial surface. Then you go down, you glue handles of index lower and lower and lower. You end up learning every time you, sorry, I have to specify that every time you study how to glue a handle, you have to specify how to map, to specify a linear map from the vector space of your manifold to the vector space of the manifold after gluing the handle. Okay. Then you do this for every index of the handles. So there are finitely many cases you have to decide to understand how to define these linear maps. You get to the one handle, and then if you are interested in building a TQFT for COB-N, so you also have to manage the zero handles, which are the appearances of balls. Okay, so the appearances of spheres bounded by balls. And so this would give a linear map from the field to the vector space of your manifold. If you are not interested in COB-N, you want to talk about COB-N-C, you don't care about this step. Finally, once you have decided how to glue the handles, how to operate linearly on the skein spaces, you have to verify the relations. That's the hard part. Actually, turns out in our case, it wasn't the hard part. So again, from now on, think about n equals, the Juhasz theorem holds in any dimension, n can be anything, but here we're using in dimension 2 and 3. So pick the n you prefer. And so a natural way to associate the vector space to an n-dimensional manifold is to take, for instance, what I call admissible colored graph in M. People also call it spin networks or spin graphs. No, string nets. So they are topological graphs decorated with combinatorial data, objects of a category, and you span a vector space out of them, and you quotient by some relations. I will be telling you more about these relations, but clearly, by the very definition, this vector space is acted upon by the diffeomorphism of the manifold, because you can move these graphs by diffeomorphism in the manifold, and clearly you stay in the same vector space, right? So it's a natural choice if you want to have a representation of the vectors of the diffeomorphism of the manifold. I'm not saying it's a smart one, but it's a natural. Now, as I was mentioning, these graphs are typically endowed with some combinatorial data, and typically these data are objects of a category. So let's talk about the categories we care about. So for this talk, the category C will always be a finite tensor category in the sense of the book by authors. In particular, it's going to be strict and monoidal and rigid, k-linear. There's going to be finitely many simple objects. Every object has a projective cover. The home spaces are finite dimensional. The length of each object is finite. It will be monoidal. I'll take it strict. I can. I'll take it rigid. Okay. So every object has a dual. And finally, I want it to be pivotal. Pivotal means that every object is canonically isomorphic to its bidual. Or stated differently, there is an isomorphism from the identity functor to the bidual functor. Finally, only if n is 3, so if I care about the 3 plus 1 dimensional case, I also require that C is ribbon. So meaning that there is a braiding and that there is a ribbon endofunctor, the twist endofunctor, sorry. Okay, any questions so far? So these are the kind of algebraic conditions. To be honest, we don't really need C to be a finite tensor category. It's a bit too much to ask for. We need less than that. In particular, we don't need C to be abelian, but actually, I mean, it's easier to talk about this case because I think everybody knows kind of what a finite tensor category is here. So as an example, I mean,
Sorry, can you repeat what you just said? You don't need it to be.
a billion. Yeah, for n equals 2, for instance, this includes all the categories which I call spherical in the sense of Barrett and Westbury. Again, they are linear, semi-simple, and they are spherical in the sense that you have a quantum trace and the left and right trace are equal for every object. For n equals 3, any modular category is going to be okay, semi-simple or not. If you want to have in mind a concrete example, take your favorite finite dimensional Hopf algebra, take it pivotal, meaning that you have a group-like element G having this property, then its category of finite dimensional modules is going to be an example for us. Even more concretely, I'm handing you one example. I mean, this is a small quantum group SL2 when Q equals I. Okay, you can work it out. It is a 16-dimensional algebra. It's pivotal. K is G. And you can work out the finite dimensional modules, the indecomposable ones. There are 6 of them. It's easy. And you can play with them. There is the trivial module. There is another module, sigma, whose square is an invertible module. Sigma square is 1. And they are one-dimensional, non-simple, a simple module, but they are not projective. I will be talking about projective in a minute. So if you don't know what projective is, don't worry. There is the 2-dimensional standard module, the one everybody knows about SL2. And of course, it's tensor product with sigma, and which are simple, 2-dimensional, and they are projective. And then there are S tensor S, which turns out to be the projective cover of 1. Again, if you don't know what the projective cover is, don't worry. And then this guy tensor C. And that's all. You cannot go beyond this list. Everything decomposes as a direct sum of these guys. So it's a nice, pretty example if you want to have fun and compute stuff concretely. You can with this example. So this is an example of what I was saying. It's a spherical, but it's not semi-simple. You see, there are objects which are non-projective here.
So, sorry.
Yes.
So are you taking the square root of -1 just to make the dimension small?
Yes. Okay. So,
2 quick questions. If you say modular, could you also take pre-modular for n equal to 3? So do you need non-trivial Müger center?
You meant do you need trivial Müger center?
Yeah, do you need trivial Müger
Okay.
center?
No, I don't need it. I don't need it. Actually, our hope is that we will find an interesting example when the Müger center is going to be
So
non-trivial.
modular is too strong. Modular is too strong.
Modular is too strong.
Yeah.
Modular automatically will give you TQFTs which are invertible, as we will see later.
And if you say spherical, non-semi-simple, there are 2 notions of spherical. One is trace spherical, that left trace is right trace, and the other one is that pivotal squares to Redford.
I meant the first one. So, okay, what is written here is something I shouldn't spend any time here. It's just saying that when you have such a category C, it's what we already seen in many talks. When you have a category C, you have a functor which is called the Reshetikhin-Turaev functor, which takes a tangle with objects of the category coloring the strands, and hands you back a morphism. So RT of this is an element of HOM. In this case, would be from W tensor U star tensor V to itself, but I could do more complicated example. I was lazy here. Here would be to U star tensor W tensor V. That's all I'm saying. So, and that is called the Reshetikhin-Turaev functor for the ribbon case. For the spherical case, you should just draw things in a disk. So everything is flat. You don't have any crossings. In that case, actually, it's more correct to attribute this construction to Penrose, even though it didn't formalize it this way, because actually this is basically where it comes from. His thesis, by the way. Okay, so now I can formalize what a C-colored graph is. It is a graph with edges which are oriented and framed. So you can think of these edges as little bands embedded in your manifold. And each edge is decorated by an object of your category. And the vertices are decorated by morphisms in your category in the standard way. I'm not inventing the wheel here. So if you've already seen this story, you're getting bored. I'm sorry. So locally, you will see something like this. If you have U, V, and W, here you should have a decoration which is F, which is an element of U tensor V to W in C. Okay, this is the kind of decorations you should have on the vertices. The only condition here I'm adding is that I require somewhere in the graph that there to be exist a projective color, and I will be telling you what I mean by projective in a minute. I mean projective in the algebraic sense, but I will recall the definition. Okay, so and I want this to happen for every component of connected component of the manifold. So the morale is that everywhere in every connected component there should be at least one projective color. These funny conditions, I will explain why later. And I consider these graphs up to isotopy and up to one relation, which is the skein relation. Now, probably you've already seen what a skein relation is. It is something happening in a ball. Here, for instance, I see this. This is a ball. I see this diagram. And suppose that I have another diagram in this, which is outside of the ball is it the same graph, but inside the ball, it's another graph with the same boundaries. But then it's more complicated. I don't know. But it turns out that if I do Reshetikhin-Turaev of this part and this part, I get the same. So RT of this, suppose that this is equal to RT of this. Then I declare the two graphs to be skein equivalent. This is a standard skein equivalence. The only proviso here is that I only accept this skein equivalence when there is an edge of my graph, which is not entirely contained in this ball, which is colored by a projective. Okay, so the morale is when locally applying a skein relation, always make sure that there is an untouched projectively colored part. Okay, an example of something you cannot do in this story is suppose that I locally have a little projective here. Okay, in the standard theory, you would just evaluate it, the quantum dimension and throw it away. But if you do, actually, you get zero. Normally in the non-semisimple case, and so this is forbidden because it's forbidden if outside there is no projective. If outside there is projectives, you can do it, but if this is the only guy surviving in your manifold and you want to throw it away, you can't. Okay, that's forbidden. I hope this is sufficiently clear. Okay, so it's a funny definition, I'll motivate it later. Now we should say what a projective is. So I am not going to get into the details, but there are a few things which are useful to know. So first of all, what is a projective? It's an object with a special property. The property is that the home from that object, it preserves epimorphisms in the category. Whatever, I gave you the definition just because I need to give you the definition, but I won't use it. So what I will use instead is some basic properties about projectives, namely, if P is projective in a category like the ones we're considering today, if P is projective, its dual is projective. And most importantly, the set of projective objects forms an ideal. So what is an ideal? It's a subset of your category, such that whenever you tensor an objective in that ideal, for every V in C, you tensor it with P, a projective, you still are projective. You get a result which is projective, first thing. Second, if you are a retract of a projective, then you are projective. A retract is a V with maps F from V to P and G from P to V, such that G composed with F is the identity of V. So it's some object whose identity factors through a projective. Whenever you have that, this needs to be a projective. Okay, so in this sense, this is an ideal. It turns out that it is the smallest non-trivial ideal in C. Every other ideal in the sense of the previous lines is going to contain the projectives, okay? Except the trivial ideal composed by the null object. This is not interesting. Okay, and another important point is that the category is semi-simple, meaning that every object is a direct sum of simple objects, if and only if the projectives are everything. If and only if the trivial object is projective itself. So these are three different characterizations for semi-simple categories in our setting. Another thing which is true is that whenever you have a simple object, you can find a projective cover. So the simple object might not be projective. Think about the identity. It is in general not projective as soon as your category is not semi-simple. But there is a projective which maps surjectively onto it. And you can take the smallest one, the indecomposable one, which is called the projective cover of the object, okay? And it is canonically associated to your object up to isomorphism. By our hypothesis, it exists in the category. So finally, we say that the category is unimodular if, when looking at the projective cover of the trivial object, which I just told you exists, it turns out to be self-dual. Okay, that's the definition. So from now on, I will suppose that the category is unimodular. Okay, the construction applies for the moment only to these categories. Questions? Yes.
Maybe a question to the previous slide. So I understand the definition of the admissible scale, but can you write a list of, say, I assume I have a finite number of strands. Can you write a list of relations, scale relations that will give me a complete list of such admissible scales?
They will depend on your category, right?
Right.
So the general answer is no. I don't know how to do it, but concretely, if you think about QQSL2, for instance, you have the Kaufman relations,
right,
and well, I don't know if I can really answer your question in the sense that you can do all the standard relations, except that you cannot, which for UQSL2 are the Kaufman relations, except you cannot eliminate all the projective colors. That's it. So sometimes they are forbidden. It's not just a local requirement, you see. Maybe locally you can do whatever you like, but unless outside there is no projective, in that case you have to be careful.
So every time I have a category, I just have to separately understand it.
Yeah. Yes. So an example now, what is, for instance, this vector space associated to the sphere S2? Let's take n equals 2, take the sphere. So what are the admissible scales in the sphere? Let's draw a few pictures. They are just graphs in the plane, because the sphere is basically the plane plus 1 point, right? They are graphs in the plane with some coupons. They can be more complicated than this, but I'm lazy, okay? But somewhere there's got to be P, which is projective. Every time I use the letter P, I mean a projective object, okay? V might not be a projective. These are coupons. So here F would be a morphism from P to V. Here G would be a morphism from V to P. That's just a very lazy example of such a scale in the sphere, right? Okay, so if you think about it, actually this graph is equivalent to one of the following form. Let me call it F prime. Why is that? Because you can look at this disk. In this disk, what I see, it's the following tangle, the following diagram. Right? That's what I see. If I straighten up the dotted part, that's what I see. And you see there is a p-colored, so projective colored arc, which is not entirely contained in that box. So here I can replace this box by a single morphism which goes from P to P, and that's what I call F prime. This is a skein equivalence which is allowed. Okay, so this is to motivate the fact that actually up to skein equivalence I can always reduce to a graph which looks like this one. Okay, so easy. But as I said before, you cannot go easier than that, because in general you cannot drop such a circle unless the category is semi-simple, because projective, the trivial object is projective, so you're allowed to do anything you want. But if the trivial object is not projective, you cannot drop this kind of thing. So that's where you stop in general in the non-semi-simple case. So what would be then, let's go back to our strategy. This is an example of a vector space associated to a sphere. What would be then a linear map associated to 100? So if I make a sphere disappear by gluing a ball, what happens? I should have a linear map from the sphere, from the skein space of the sphere to K. So the theorem is that actually the datum of such a linear map is exactly equivalent to the datum of what is called a modified trace on the ideal of projectives for the category. So it's nice because it's matching topology to algebra, if you know what a modified trace is. If not, I will tell you. But the idea is kind of easy. Look at this picture, for instance. So let me maybe give you the definition of modified trace and then discuss why this theorem, So a modified trace is a way of assigning scalars to every endomorphism of every projective object. So it's a list of traces, which I denoted MTRP, which take a projective, an endomorphism of projective, and give you a scalar for any projective. So it should be a trace in the first sense. So it should be cyclic. So if you have a map from P to P prime and a map from P prime to P, you have two ways of composing. You get either endomorphism of P or endomorphism of P prime, and you want the two endomorphisms to have the same trace. That's a natural condition for a map to be called a trace, right? The second is probably less obvious, and the picture goes as follows. Suppose that you have P tensor P, B is any object, P is projective, and you have an endomorphism F. Since P is projective, this tensor product is projective. So this you can do the M trace of V tensor P for this endomorphism. But you can do also another thing. You can also decide to partially trace out V and remain with a single endomorphism of P. And you want to ask that this is equal to that. Okay, this is the property of left modified trace. You imagine the right modified trace is that V is on the right and you trace on the right. Okay, a modified trace has to be left and right. Okay, so what's the relation with the topological thing? I said as soon as I can evaluate my graphs in the sphere, then necessarily I have a modified trace, and reciprocally. Well, what is going to be my modified trace? I just told you that I know how to evaluate graphs in the sphere. So I take this graph. I want to get the trace of F prime. Well, the value of this graph is going to be the trace of F prime. Okay, why is it cyclic, for instance? Easy. Look at this picture. Let me put here P prime to have the same notation as before. And then the value of this graph is an isotope invariant, right? So it's going to be a number, and I can look at it as an endomorphism of P prime to itself, if I move this box up to isotopy here, or as an endomorphism from P to P, if I move this box up to here. So cyclicity is clear. And then this relation is also clear. I like to think about it, but it's also clear by the properties of the graph invariants. So in a sense, if you have the graph invariant, so the scalar map, then you have a modified trace. That's easy. More difficult is if you have a modified trace, then you have such a linear map. And that's exactly why the modified traces were invented in the first place by Geer and Patureau, and also in collaboration with Turaev. And they were also developed in collaboration with Juhasz. Any questions so far? Okay, so the question still holds: can I do gluing of maximal index handles? Can I fill the spheres with balls? Can I make those spheres disappear? Do we have these linear maps? Yes, if and only if I have modified trace, and hopefully, fortunately, modified traces do exist under our conditions. This is a theorem by Geer, Kujawa, Patureau. Actually, they even prove more. Not only such a modified trace exists and it's unique up to scalar, it is non-degenerate, which is something we're going to use in a minute. It's non-degenerate in the following sense. Whenever you have a projective, you can consider the home space from P to the trivial object and the home space from 1 to the object. So if you have a morphism here and a morphism here, you can compose them, you get an endomorphism of P. And if you have a modified trace, you can compute it on that endomorphism, you get a scalar. So this gives you a bilinear form on this vector space. And for the modified trace to be non-degenerate means exactly that bilinear form is non-degenerate in the sense of linear algebra. Okay. So yes.
So the key, like the previous hypothesis here, is the key one the unimodularity of the.
Sorry, I don't.
Like, does it require unimodularity to because?
Yes, this theorem. For this theorem, yes.
There is no way around it.
No, there is. So if you don't have unimodular, you might have left trace and right trace, but they do not necessarily coincide. And there is a theory which has been developed by them.
If it's not unimodular, it will not be cyclic. It will be twisted cyclic, right?
Well, maybe you're right. It's not just about
for cyclicity. You need actually if and only if. I mean, in some cases you can prove that it's if and only if.
You're right. Yeah.
But there is
another non-unimodular case I wanted to mention. They developed a theory, but it uses the distinguished element, which is basically the head of the projective couples of the trivial. It's a different theory for which we don't have associated topological application yet.
That's why, and in non-unimodular case, we showed it for example, in Hopf algebra case, all the time you have a trace, but when you move, it's not cyclic, but you will have action by this invertible distinguished element. So when you move morphisms around, you might get something like sign. Could it be used for invariants of some bundles?
It's a very good question. We spent a lot of time on this kind of question and couldn't come up with the correct topological structure to make sense of it. But it's absolute. I am convinced that there is an answer to your question, but I don't know it yet. I spent a lot of time thinking about this. But.
So can you repeat your hypothesis on your category C again?
So it's a finite tensor category, pivotal. What else do I need?
Unimodular.
And unimodular. Yes. Okay, so now I have this. So I know how to glue n+1 dimensional balls. So I know how to evaluate graphs in the sphere. So, oh yeah, a comment about these modified traces. Why one does care? This is actually what I just told you is the reason why they appeared in a sense. Okay, they appeared because one wanted to evaluate graphs in the sphere, and if you do the standard Bayesian of Reshetikhin-Turaev stuff, as soon as you have a projective color, you get 0. So you lose very much of the objects of the category. You are not able to detect them. Okay. So the modified trace was exactly invented in order to get numbers out of colors of your category, which are not the simple ones you would normally work with in the standard, in the initial theories. The price to pay is that the modified trace is defined only on projective ideal. So when evaluating it, you must make sure that your graph contains at least one projective color, in the sense that your graph is projective, in a sense. And that's why we define this K-mean space in that funny way. I require that every component contains a graph, a color which is projective. And that's also the reason why in the admissible scaling relation, I required that there is a projective hanging around somewhere, okay? So I want to make sure that I can always do my modified trace business here. Okay, so now we go to one handle lower. I want to glue an index n handle. So think about n equals 2, and that is the picture. You have your surface, and this is what it's going to look like to glue a handle of index, in this case, would be 2. So basically, I'm contracting a disk, and I'm getting 2 Haas spheres. That's the operation in topological terms. So I want to this operation, I want to associate a linear map from the skein module before the operation to the skein module after the operation. So I want to associate to any skein some skein after the operation. How do I do that? Well, I told you that the modified trace is non-degenerate. Therefore, there is a non-degenerate duality between Hom C P1 and Hom C 1P for every projective object. Who's going to be P in my picture? P is the tensor product of the 3 colors I see here. Okay, so I fix a basis for these 2 vector spaces, a dual basis and a dual basis, and I call the sum of xi composed x upper I call it lambda P. It's an easy exercise of linear algebra to check that this does not depend on the choice of the basis I fixed, and it is natural. Natural in P, I mean. So I can define a map like this. Okay, and we call it the cutting map. And lambda is called the cutting morphism because basically what it does is it takes the identity of your P and kind of factors it through the trivial. It doesn't factor it, it's not equal to the identity, but it's something you apply to the identity morphism, you replace it by another morphism which passes through the trivial object.
Sorry, so which dimensional handles do you mean? So before n it was a dimension, yes. Now n it's
here I'm taking the index n handles. So if n is 2, it's 2 handles. If n is 3, it's going to be 3 handles.
It's 2 times s1. Yeah.
So if n is 2, I'm gluing a 2 disk to my surface along an S1. If n is 3, I'm gluing a 3 ball to a 3 manifold along an S2. Okay, it's harder to imagine what I'm doing topologically in dimension 3, but it's you know, you have a sphere and you have some graphs intersecting transversally, and you do the same kind of operation locally. You replace the sphere by 2 balls. You cut along the sphere and you replace by 2 balls. Okay, so that's what I do for n handles. Then I have to go. Oh, so turns out that this operation is well defined. Okay, it's not trivial. There's something to prove.
So how do you choose P? M does not depend on P, right? How do you choose P?
That's a good question. It depends. So it's an operation I apply to every element of my vector space. So it's a linear map, right? So I take my vector in my vector space, which is given by a blue skein here. So it intersects my green thing, and I apply my operation. What is not trivial here is that actually what I'm describing here is well defined, meaning that a priori I could have moved my graph to intersect differently my green curve, but yeah, it works. It's well defined. Okay, so the next step would be to glue n-1 index handles, which in dimension, I don't know if you can see the picture. On the left, it's a surface. If you glue a 1 handle to a surface, you're basically choosing 2 disks and connecting them by a tube, okay? So you should imagine that you want to map a skein before the operation to a skein after the operation. So that's easy, you might say. I just avoid the 2 disks where I glue the tube. I push a little bit my skein so that it doesn't touch those disks. I do my tube and the skein is there. So I just map it to itself. Yes, but you know, you made an isotopy to avoid the 2 disks where you're gluing the tube. So you need to make sure that if you do the other choice, you get the same thing, which is not true in general. They are not isotopic after the operation is done. So this is not well defined a priori. The idea is that suppose that I hand you a special skein on which you can slide upon. I call it the red skein. Okay, and that's actually, you can see it on the core of the tube. What's this property? The property is that when I say I can skein on it, I mean that I can slide on it. I mean that this is the skein, and I can take any other skein and I can modify it. So this is I suppose that it is such that the first one is skein equivalent to this one. I can always pass the blue thing over the red. Suppose that you have such a thing, then you're happy. right? You take your blue thing, you push it so that it doesn't touch the base of the tube, and then in the core of the tube you put such a red skein, and you're happy because it's going to be well defined. You can pass over this red in order to avoid the disks.
You require this just for a loop of a red skein, or
Yes.
could there be anything inside the red loop?
Just for even an unoriented red curve, simple closed curve. That's all I need. So, yeah, the problem is, okay, give me this red thing. I need to have a skein which has this property. So how to make sense of such a red skein? Can I find such a skein? So if you're familiar with the standard semisimple theory, the answer is cubicolor, namely exactly what Ingold was using in his talks, namely you consider the direct sum, the direct sum of all the simple objects of your category multiplied by scalars, which are their quantum dimension. That's actually, this is what topologists call the cubicolor. You can slide on it and everything is fine. But in general, it doesn't exist. If the category is not semisimple, this doesn't exist. So the idea we found is the following. It's true that you start with a graph T. It's true that you can find a way of making sense of the red, and I will tell you how, such that you can slide over that skein. So what is the way of making sense of the red? It is the following. You push a part of your T graph, of your graph before the handle. You push it along the handle near to the red. You color what was red by the generator of the category. And that's an hypothesis I'm making. I have a generator of the projectives of my category. I will tell you in a minute what it is. And then you put a coupon, which I call the chromatic morphism. And this is the key thing here. So I should tell you what the generator and the chromatic morphism is. So a generator is just an object, a projective object, which is basically, think of it as the direct sum of all the projectives in the composable, okay? So asking that such an object exists, it basically amounts to say that the ideal of projectives is finite dimensional, it's finite. You have finitely many indecomposable projectives. So it's a kind of finiteness condition here. And what is a chromatic morphism? It is by definition a coupon from G tensor G to itself, so a map from G tensor G to itself, such that this equality holds. It's a funny equality. Remember that this is the cutting morphism, so I could have drawn it as two separated boxes. It was introduced like 2 slides ago. Now, you might wonder where the hell does it come from? If you think about it, if you stare at it quite a long time, you will understand it's actually coming from the requirement that you want 2 handles to cancel with 1 handles. Topologically, that's the reason. So whatever it is, it does exist. Theorem, that's the algebraic paper I was mentioning at the beginning. If you have a finite tensor category with modified trace on the projectives and a unimodular over an algebraically closed field, then the chromatic morphism does exist. So it's not, you can find it. Examples, as I said, the semi-simple spherical categories. In that case, what is the generator? As I said, it's the sum of all the simples. And what is the CG is, oh, yeah, I forgot. It should be an endomorphism of SI tensor SI. So it's actually, yeah, I miswrote here. So it's the sum of the identities multiplied by the quantum dimension. I'm sorry, this is miswritten. So in another case, which is not semi-simple in general, you take a finite dimensional Hopf algebra H, and then if you think about it, G is H itself, it's seen as a left regular module, right? It's a projective module, and it actually is the generator, a generator for the ideal of projectives. And then you need the map from G tensor G to itself, so from H tensor H itself as a morphism of modules over H. Turns out that this is the formula. It's ugly, but it does exist. It's explicit. Yes.
Do you in general assume that the category has enough projectives?
Yes.
Okay.
Well, he says finite.
Yeah, it's a finite.
So
for today it's finite, but in general we would assume.
Because it's a finite, it's a bit of an overkill.
Yeah. As I said at the beginning, we don't need actually finite tensor category, but even if we don't, we ask that. So why this funny chromatic thing will solve our problem. Let me show you that one can slide on reds. This was the key property why I sold you this chromatic thing. And indeed, how do I make sense of the red? By definition, this is how I make sense of the red. And now I want to slide on it. Suppose I have a, so am I too long?
How much time do you need? Because it's already.
No, I can close rapidly, so I don't motivate maybe this. I just want to go to the final thing. Once you have this chromatic, you're left to, once you have this chromatic, you already have done the list of handles moves to get a 2 + 1 dimensional theory. And so you have these two Reviro theories. You have everything to do with the Reviro theories in the non-semi-simple case. It turns out that they can be extended to full cobord TQFTs if and only if the category is semi-simple. When you want to consider 3 + 1 theories, you still miss how to glue one handles in dimension 4. And that's related to what happens when you compute this thing, this endomorphism, and it turns out that it does. So the condition, there is another condition we have to impose in order for it to be able, for us to be able to define the linear map associated to such an handle. And the condition is that we should be able to find a certain endomorphism of the projective cover of the identity, which has this property. Delta 0 is this thing, and the composition should be equal to a scalar, non-zero, times the cutting morphism of the P. It's an explicit condition. It turns out that it does exist as soon as this endomorphism of P1 is not true. Okay. Basically, the way you use this G, this gluing morphism, is basically that when you glue a one handle, you're connecting two parts of the manifold by a tube. Well, you take one of the two parts, the other two parts, and you connect them by this gluing morphism. You can always make sure that in your graph there is a P1 hanging around. That's an up to scale equivalence. This is true. Okay, and then the theorem is that for a 3 + 1 case, as soon as you have such a gluing morphism, which again it's the fact that the delta 0 P1, this endomorphism of the projective cover of the unit, is non-zero. As soon as you have it, you have a non-compact 3 + 1 TQFT. It does extend to a full compact TQFT if this not only delta 0 P1 is non-zero, but it's actually multiple of the cutting morphism. And that's the case we call a compact category. You can even ask more. You can ask that the same morphism is same scalar times the cutting morphism for every projective, and that's what we call the factorizable case, because it does indeed coincide with the factorizable for the modular categories in the standard sense. And in this factorizable case, the theory is invertible, but we have examples where the theory is not invertible, so it is strictly beyond the modular case. And the case where it's not invertible and over is the case where we take a group algebra, non-Maschke case of finite field, and the order of group divides. So it's still a symmetric monoidal category, but it's not semi-simple. So topologically, it's not going to be very interesting, but still the TQFT is not invertible. I'm gonna stop here. Sorry.
Still, it's time for questions.
Yeah. So actually, like Christophe was asking earlier, if you want something non-invertible, you can just take craniator with a premodular category. It's semi-simple, and it's gonna be non-invertible.
So you say if you take craniator with a premodular category,
yeah,
you're gonna get what?
Well, it's non-invertible. While still being semi-simple.
Yeah, but it's still known to detect just Euler characteristic.
Yeah, no, but then that's another
Yeah,
question. Indeed, it's like then you have other requirements. Maybe like you want something that indeed that is more sensitive.
That's mostly controlled by the Muger center. Then.
Yeah, exactly, and this is symmetric category, which is usually.
So what you get is still doesn't have any potential to detect this.
Yeah.
So if there are no immediate questions, then lunch is today in the cathedral. And since it was not announced in some version of the program in the correct way, our next and final talk for today is at 2:30. We will announce then how to go and when to go to the rest. Okay, but let's thank both speakers of this morning. Sorry, that was